And we're on to the next speaker, Michael Briggs.
Okay, thank you. So I'm going to talk about Fermi Gamma Ray Burst Monitor, and it's an excellent instrument for observing transients in this multi-wavelength, multi-messenger era. And I'll also particularly talk about the Gamma Ray Burst 1708-17A, which you've already heard. Of course, it's a multi-institute and multi-member team project. So the slide on the figure on the left shows you an image of Fermi with the main instrument, the Large Area Telescope, which measures high-energy gamma rays on the left, and lower underneath, half of the detectors of the Gamma Ray Burst Monitor. We have the low-energy or sodium iodide detectors, which are a total of 12. They point in various directions and measure gamma rays from about 10 keV to 1 MeV. They're pointing in different directions, so we can approximately localize the sources by comparing the signals. A source face onto a detector will make a stronger signal in that particular detector. We have our medium energy detector here and another one on the other side with bismuth germanate. Fermi GBM is an excellent instrument for gamma ray context observations with this broad energy range. We have high uptime, only being off when the Fermi is in the SAA, a very wide field of view, basically only missing the sky blocked by the Earth, which means that a particular point of the sky is observed on average 60% of this time. We provide triggering where bright transients are promptly detected in orbit, and we have high resolution continuous data which can be used to search for weaker transients or provide context observations for any source that you're interested in. We have several source detection measurements. I'm going to talk about a variety of sources in the next few slides. Short transients can be detected by triggering, where the software in orbit detects a rate increase, or they can be detected offline by a ground search of our continuous data. And I should say here that a short versus long is defined by a comparison to the background variations. This instrument is moving in low Earth orbit, and it causes the background to vary on a minutes time scale. So it's easier to find things that are shorter than that kind of time scale. We have to use different techniques to find longer transients. So very long persistent sources can be found by the source rising or setting against the edge of the Earth, or long period pulsars by a pulsar phase folding technique. Some of the sources we find by triggering, because they made rapid transients. This is a time history of the triggers we've seen, are gamma ray bursts, particle events from the Earth's magnetosphere, terrestrial gamma ray flashes, soft gamma repeaters, solar flares, and a few other sources, galactic transients. You see the rate varying. That's because some of these sources are variable in long-term timescales, like the solar cycle, or SGRs are. Some of them are episodic in their activity. Some of the variation is because the software on board is improved, which has changed the detection rate of terrestrial gamma ray flashes. We now have more than 6,000 triggers over the about 9 years of the mission. That includes more than 2,000 gamma ray bursts. This figure here has already been mentioned that there's two types of gamma ray bursts. This is the distribution of the durations, showing that there are short and long gamma ray bursts. We have about 200 per year of the long type and about 40 per year of the short type. So GBM has currently the highest detection rate of the short gamma ray bursts, which are very interesting as counterparts to merging neutron stars and gravitational wave signals. Getting to some of our other source classes, I mentioned the Earth occultation technique. We use that to monitor 200-some sources, from X-ray binaries to AGN. There's been so far 102 detections. A notable one is monitoring the Crab Nebula and showing that there's long-term X-ray variation. Previously, this source was used as a standard candle, and it's been shown not to be that. There's a URL there that you can go and check to see whether your favorite source is monitored, and you can make requests for monitoring. We monitor long period pulsars, which tend to be accreting pulsars, and 38 of these have been detected, and another URL for that. You also see type 1 X-ray bursts, of which in a 3-year period that we were studying this phenomena particularly, and there's a paper, 671 were detected, and we were able to study the recurrence pattern of this burst, particularly with the wide field of view and with the long time period monitoring. Another source type, not astrophysical, that's interesting to me is terrestrial gamma ray flashes. These are gamma ray emission by thunderstorms, extremely brief flashes, shorter than gamma ray bursts, typically shorter than a millisecond. You see here an example that's about 200 microseconds long and emitting gamma rays up to 30 MeV. We know they're from thunderstorms and correlated with lightning. You see complicated patterns where they're following coastline and so forth. Here's some following the Marshall Islands atoll. It's the coast of Australia, some of the islands in this region where we're located at. It's particularly interesting. Here is Singapore. This is actually an extraordinary concentration in the Malacca Strait here. There are 8 here, which may not seem very much, but out of a total sample of 1,300, that's quite a concentration. This is one of the highest concentrations in the world. As I mentioned, TGFs tend to be near coast, so you actually have 2 coasts close together, and it makes that a very favorable location. So this would be a good spot for ground observations of terrestrial gamma ray flashes with that very high rate, if anyone was interested in that. Magnetars or soft gamma repeaters, related, of course, to high magnetic field pulsars that have already been mentioned. There's a variety of papers about that, some unusual phenomena. You can ask Krista Covoluto more about that. We're always interested in supporting other observations. GBM has been involved with some target of opportunity campaigns with NICER. So the triggering on 4U0142 plus 61, accreting pulsar, and another X-ray burster, providing gamma ray context observations for these sources. So let's talk about the gravitational wave source 170817 and the GRB. You've already seen this figure, but if it works, where's the mouse? If it works this time, you'll have sound. So. So what the previous speaker doesn't mention is from the gravitational wave side, it was extraordinary how long the chirp signal lasted as a neutron star binary. They were able to follow it very long. And then there was this 1.7 second delay between when LIGO lost the signal and the gamma ray burst, which was observed by GBM. And you see 2 different energy ranges here. And it was also detected by the anti-coincidence shield on the integral spacecraft. And let me mention, it was triggered, and so there's automatic processing. We get a tremendous amount of data from GBM, and we try to do as much of the processing automatically. So it was the definition of the trigger is the end of the data time, which contained the rate increase. And the flight software noted that 2.4 milliseconds later. And it's automatically processed on the spacecraft, sent down to the ground as a priority notice, and that was automatically transmitted to any interested scientists 14 seconds later. And the flight software made a location that was transmitted to interested persons 25 seconds later, and then a more accurate location was made 38 seconds later, and the LIGO team noticed this, and even though their data had that glitch, identified that as highly interesting, and things became extremely exciting to us on the GBM team 40 minutes later. Actually, a little bit before that, we were emailed. So it was a very exciting day. And it was interesting because this gamma ray burst, we would have normally not have given it a second thought. We now have, we get 40 of these per year. This one was, besides being intrinsically dim, as you've heard, is fairly dim in apparent appearance. And we would not, with 40 of these per year and 9 years already, we would have not really given it a second look. So it only becomes extraordinarily when the gravitational wave counterpart and taking a deeper look. So it really looks like a pretty normal short gamma ray burst. It's about 0.5 seconds long. It's definitely significant in the GBM data. It's clearly detected in at least 5 GBM detectors at greater than 3 sigma significance in each. If we take a deeper look, we fit it with a power law with an exponential cutoff, and that gives us a characteristic peak energy of 185 keV, which is rather low for a short gamma ray burst. So it's coming out to be kind of weak, when we know the distance, it turns out to be kind of weak. It's a little bit low energy, but not completely out of the ballpark. And what also turns out to be very unusual is there's this second pulse, which is consistent with a black body emission, which is pretty unusual, actually very unusual for a short gamma ray burst. And there's been a lot of theoretical interpretation of that. Anyway, in terms of the joint analysis, knowing that it's a gravitational wave source, the chance probability association is extremely low, so the association is unambiguous, which confirms that at least some binary neutron star mergers are progenitors of short gamma ray bursts. And from fitting the pulse shape, we have the delay to the start of the gamma rays is 1.74 seconds, which just that simple fact allows us to deduce a surprising amount of science from that one simple number. It gives you a constraint on the speed of gravity, comparing the, if we just assume that all of that time is a delay between gravity and light, it gives you a very tight constraint on a difference between the speed of gravity and the speed of light. It gives you a very tight constraint on violation of Lorentz invariance. It tests the equivalence principle by the fact that the signal passed through the gravitational field of the Milky Way, and other papers have appeared saying that it also even tighter constraints because the gravitational wave particles pass through the gravitational field of the Virgo cluster. It can be used to get constraints on neutron star equation of state. And we can then proceed from fundamental physics to gamma ray burst physics. And so there's several popular models about gamma ray burst emission. And so with the internal shock model, it's entirely consistent with that model. And you can set upper limits on the radius of the jet and the emitting region, which are all plausible. In the external shock model, it's also plausible, and you can set limits on the size of the deceleration radius. The thermal tail is more unusual, as I said, and you can explain it as arising from photospheric emission, or what people are calling cocoon emission, a less relativistic emission. comparing it to other gamma ray bursts, we know the distance. We can calculate the isotropic equivalent energy, and this is just assuming that you have that same gamma ray emission in all directions, which we know is not true, but it's the standard approach. And it makes this gamma ray burst 2 orders of magnitude closer than any other known gamma ray burst with a distance measure, and 2 to 6 orders of magnitude less energetic. So it's extraordinarily different than our population of known gamma ray bursts. And the most likely explanation for this is that we're observing it fairly far off axis, which is consistent. I'm seeing a lot of head shaking. We're observing it fairly far off axis, and most of the sample is being observed on axis and observing it with the so-called structured jet. The bulk Lorentz factor is a function of the angle from the axis of the jet and decreases as you move away from the jet. And there's, of course, there's an observational sampling effect that a intrinsically brighter jet being on axis can be seen farther away, and we tend to see more intrinsically brighter bursts because they can be seen farther away, and this intrinsically dimmer burst, at least at this angle of observation, is less likely to be observed because it has to be nearby in order to be observed. And in that sense, we were lucky to observe this one, but of course it's selected, instead of being selected by being able to measure its redshift, it was selected by having a gravitational wave counterpart. So there may be other gamma ray bursts like this that, without knowing that they had a gravitational wave counterpart, since that observation didn't exist, look boring in the current observational database of gamma ray instruments. So we have a unique observation telling us to look at this carefully and determine its redshift. So this also tells us that since we haven't seen gamma ray bursts like this close before, it's telling us that there's an existence of a population of subluminous short GRBs that hadn't been taken into account before, whatever your explanation for it is. And this causes us to reassess the spatial density of short gamma ray bursts and to calculate a higher joint rate of GBM and LIGO detection rate. And in the paper the teams wrote together, we expect, still a large uncertainty, that in the next observing run that there should be about 0.1 to 1.4 joint detections per year, and at the design sensitivity you heard about for LIGO Virgo, the expected joint detection rate increases to about 0.3 to 1.7 per year. And another realization that changes our understanding is previously we thought that the gamma ray instruments were detecting gamma ray bursts farther than the LIGO horizon, but that's actually not true for this particular event. The gamma ray LIGO can detect this event farther away than the gamma ray instrument. So the gamma ray instrument, the gravitational wave sensitivity is no longer the limit for this class of events. It's the gamma ray sensitivity that's the limit on the detection rate for this class. So the GBM team was already working on this project. We've been, as I'll talk about more, we've been working on increasing our sensitivity beyond what I've talked about detecting GRBs by triggering the triggering method of the instrumenting orbit by searching the data on the ground to increase the sensitivity by finding weaker events, which will help with this issue that now the gamma ray sensitivity is the limit on the joint detection rate. Let me turn to another source, which we don't want to forget. Earlier there was this gravitational wave detection of a black hole, binary black hole merger, 1509-14. We reported a weak gamma ray transient 0.4 seconds later. This was detected as a weak signal, quite weak signaling 10 sodium iodide detectors. The reason it appeared so weak, and actually both of the high energy detectors, the BGO, is it came from underneath Fermi. So it was a poor geometry for the GBM instrument. So it's consistent with, as I said, it's consistent with the source underneath Fermi. It locates close to the Earth. The issue is that GBM was originally designed for a particular amount that the Fermi spacecraft would tilt with respect to the Earth. And for various reasons, the spacecraft now tilts more. And so that puts some sky farther away from the axis of Fermi than GBM was designed for, which puts it into a spot that's sort of behind the instrument. So we don't get a good view of this location from any particular detector. It's seen poorly by many detectors. The signal's definitely there. We calculate a probability that it's a chance association with the gravitational wave source of 0.2%, which is not highly significant. We do not claim this as an association. We just say this is the probability, and that's what it is what it is. And for us to really to really find out that black hole mergers make gamma rays is going to take another observation. It's very tantalizing. It's a low probability, but it's not definitive. And that's the situation with this. Here's a graph that you can see that shows the signal, a small excess in many detectors. So I'll return to the topic of finding weaker signals. So we have many cases, or I say 4 cases. So the ideal case is what we have is 1708-17, that it's brighting, the source is brighting both gamma rays, GBM, and in LIGO. The other scenario, which we just saw, was that it's below the trigger threshold and it's quite weak in GBM, and it's brighting LIGO. If we have a distant gamma ray, it would be a typical gamma ray would still be bright in GBM, but it would be weak in LIGO. That would be a case that maybe knowing that a gamma ray burst happened at that time and the approximate direction, that the gamma ray detection could help LIGO pull it out of their data. A more difficult case is it's weak in both detectors, but maybe we could struggle to do something with that. So we have 2 searches underway. They're both working and running automatically. The so-called targeted search uses a detection from another instrument, and the detection happened at a particular time in a particular direction, and it knows that there should be a particular pattern of signal strengths in the 14 detectors, and it uses likelihood to test for the presence of that signal pattern with 3 different spectral templates, and compares that to an empirical record of how often we see such signal strengths for an empirical false alarm rate. And there are 2 papers about this. The other search is the untargeted search, which just agnostically searches the continuous GBM data, binning it up, and making a background model and looking for excesses and testing for an excess in 2 or more detectors. And it is finding weaker events that aren't found by the software in orbit. Some of these events have been confirmed by other instruments, SWIFT, MAXI, the integral, and one of them recently by an instrument you'll hear later, the InSight HXMT. And these events are distributed through the GCN. When we receive the data, this has a delay of several hours. It's automatically processed. Anything that's found is distributed. An example, this event was found being visible in multiple GBM detectors. It just happened at this time. It was detected several hours later when the data arrived. And it was confirmed by Insight HXMT, who wrote a circular saying that they had seen this event as a gamma ray burst. And what this means is an example using GRB 1708-17A. That event could have been dimmed. The maximum significance of that was 6.25 sigma by the way the trigger works, and therefore that event could have been dimmed by a factor of 0.7 and still triggering orbit. The untargeted search could have found it if it was a factor of 0.5 dimmer. It, in fact, did not trigger it because it had rejected that interval as having a bad background because the Fermi was approaching the South Atlantic anomaly. The targeted search could have dimmed it by even dimmer by 0.43. So this is an example of how these searches would increase the sensitivity. And we're still working on making these searches even better. So GBM, we think, is an excellent instrument for multi-messenger observations. It has a wide field of view and a high uptime. It's the most prolific detector of short GRBs with 40 triggers and of order 80 more from the sub-threshold search. We have prompt detection and distribution of the triggers, classification and localization, a wide spectral coverage, and high time resolution, and we're trying to enhance our sensitivity with these sub-threshold searches to try to get the most highest joint detection rate we can, and we're interested in helping anyone who wants to monitor other sources. You can get our data at the Fermi Science Support Center, ask for help there, and if you need more in-depth help, you can ask anyone on the GBM team. If you want questions about a particular source or how one of these monitoring services work, we're happy to help.
So thank you. Do we have any? Roger, up there.
Hi, I go. Thank you. Yeah, from your GBM perspective, what do you see the prospects for the LAT being able to contribute to this? Obviously, they're going to see far fewer events, but do you think they'll see any? Because seeing the higher energy gamma rays would be very diagnostic of what's going on.
The LAT has detected some short gamma ray bursts, notably 09, 05, 10, so it's possible.
I was thinking about the gravitational radiation. Yes.
So that was a short gamma ray burst, which was presumably emerging neutron star system. So I'd say it's possible. The rate is the field of view is smaller, so the probability is just a matter of probabilities, and they see the brighter one. So you're multiplying a factor less than 1 and another factor less than 1. So we'll have to be lucky, but it's possible. That's per year. So let's hope so. Maybe Julie will say something on her talk on the last day.
Well, I can do now that you've asked me to.
As one of the older people in the audience, I dare to say that this is certainly not the birth of the multi-messenger astronomy. We had 87A with neutrinos, gamma rays, optical, everything. So it's not the birth, it is a nice continuation.
See.
You mentioned that the most likely, if I quote you correctly, interpretation of these gamma rays was a regular gamma ray burst seen off axis. In order for this interpretation to work, you need that the gamma ray burst should have had a peak energy of about 6 MeV. So I wonder how many regular short gamma ray bursts have a peak of about 6 MeV.
There are.
I'm saying about typical. What is the typical peak energy of a regular gamma ray burst, and how many have peak energy of 6 MeV?
A typical peak energy is 500 keV to an MeV, and time resolved, it's routine to have time intervals above an MeV. I would not say that 6 MeV is normal. I don't know why you're saying that 6 MeV is necessary, but.
Well, this is a very simple calculation. I can show it to you later.
Okay.
Well, I don't think we're off by a large factor. We're off by from what you.
Could I just ask about whether these subluminous or subthreshold GRBs could be correlated with radio observations, where you have a much bigger time window, but presumably quite localized point sources, radio point sources, to see if any of those are binary neutron star coalescences.
They could. I'm not sure how sensitive that would be.
Do I see any more hands up in the air here? There.
Just to comment on the last question, there's actually a radio survey underway, the VLS Sky survey, and looking for nearby relativistic explosions that were not on axis. It's a major focus of that. So I think that's actually a route that's already been pursued, and I hope to, in the next year or so, it's much, much wider and deeper than previous attempts to do this. And the strategy is very similar to actually what you do for LIGO. You try to look for radio sources coincident with nearby galaxies, and then you do your sub-threshold comparisons afterwards. So I think in the next year or two, hopefully.
Okay. If there are no more questions or comments, let's thank the speaker again.